Okay, welcome to part 2 of the video that I'm doing to describe how to compute noise in op-amp circuits. In part 1, we talked about the idea that we model the noise generated in the op-amp itself and the noise generated in the resistors by noiseless op-amps with a noise source. In this case, it'll be a voltage source connected to the non-inverting input. Again, that's called an input referred noise source. And the resistors we model as noiseless resistors in series with the voltage source. So let's actually do that. And what I'll do here is chop out the real op-amp and replace it by a noiseless op-amp. I guess in our world, noiseless op-amps are green. And we have the input referred noise source connected to the non-inverting input, and the inverting input is connected to the resistors. Okay, and we'll call this Vn. And we talked in the last video about how to get Vn, which is a function of the op-amp as well as the system bandwidth. So we talked about how to get Vn from the op-amp spec and the system bandwidth. So let's also chop out the resistor here, the real resistor, and let's replace it by a noiseless resistor and a voltage source. And we'll call this voltage source Vf. This is Rf. Okay. And finally, we'll chop out this real resistor here and replace it by an ideal noiseless resistor and a voltage source. So this is R1 and V1. And in the previous video, we showed how to determine the values for V1, Vf, and Vn. Okay, so what we want to get is the total noise output at the output of the op-amp circuit due to each of these three different noise sources. So again, we've got the op-amp noise, we've got the noise due to R1, and the noise due to Rf. Now, again, these are RMS values, and so we can't just do the analysis and add everything up. It turns out that doesn't work. What we want to do is find the op-amp, or find the output voltage for each noise source in turn. And because they're noise voltages, when we get this RMS value, we will get the total output noise by summing the square of each of the RMS voltages and then taking the square root of that. So that's what we will do. In order to make this work, well, I guess the very last thing we need to do, because we're interested just in noise, we will assume that the input voltage to the circuit is 0. So we'll assume that we don't have any source voltage connected to the circuit. And so if there's no source voltage, then all of the voltage at the output is now due to the noise sources. So that's the analysis that we will do. We will begin by, I guess we'll find the output due to the noise in the op-amp. So in order for that to happen, we will, whoops, that's not quite what I had in mind. Okay, we will take this noise source and set it equal to 0. which is just a short circuit. And we will take this noise source and set it equal to 0, which is also a short circuit. And now we want to find the output voltage due to the noise at the input, the non-inverting input of the op-amp. So I'll call this, say, V out sub n. Okay. Again, this is the now the output voltage due to the noise at the input referred noise that the op-amp generates. Okay. So if you look at this circuit, it turns out we don't have to do any analysis because this is exactly the same circuit that we analyzed in part 1. Oh, actually, we analyzed this in a previous video showing the non-inverting op-amp circuit. But remembering or noticing that this Vn, this guy here, is essentially providing a voltage between the non-inverting input and ground, we see immediately that this is just an input to a non-inverting op-amp configuration, so the gain is going to be 1 over Rf, or 1 plus Rf over R1 times Vn. So what we see is that the output voltage due to the noise of the op-amp just has the non-inverting gain applied to it. So that was easy enough. Well, let's get rid of the noise at the input of the op-amp. And let's reinsert a noise source for R1. So there we go. We've reinserted the noise for R1. This is V1. And now we will see what the output voltage due to the noise generated by resistor 1 is going to be. Now you'll notice this circuit is actually different than the non-inverting op-amp configuration which we had before. So we will have to do some op-amp analysis, which I always think is a good thing because it's so much fun. So to do the op-amp circuit analysis, again, the idea is that the output at this point, the op-amp output, will be whatever it needs to be in order to make the non-inverting and the inverting input voltages the same. Now you can see that the non-inverting input is connected directly to ground, which means then that V minus, which is going to be set equal to V plus by the fact that the output will be whatever it needs to be to do that, will be 0 volts. So what that says is that at this point in the circuit, my voltage is 0 volts with respect to ground. Okay, this seems kind of strange, but what that means is that, well, one way to look at it is that the voltage across R1, you can see I go from 0 volts here to a voltage of minus V1 at this point. Okay, because again the negative input is 0 volts. So I'm at minus V1 here, which means that the voltage across R1 is minus V1, which in turn means that the current, we'll come up with a sort of uglier version of red for the current going through resistor 1 can be written as I1 is minus V1 over R1. Okay, and again this is a consequence of the fact that the voltage at the inverting input is 0, and so in order to make that happen I have to have the voltages, the voltage source and R1 have the voltages that we've indicated. Now you'll remember that in the ideal op-amp model, the current going into the inverting input of the op-amp is 0. So this guy is 0. So that means that all of the current that flows through R1 also flows through RF. So this is the same as I1, which in turn means that the voltage across RF, which I guess we could call VF, will be VF is equal to RF times I1, which is equal to minus V1 RF over R1. Okay, so that basically says that the noise generated by R1 is actually processed by the gain of an equivalent inverting op-amp circuit. It's kind of weird. Okay, so hopefully things are still making sense. Let's get rid of this voltage source, or we'll just get rid of this whole chunk of mess. Redraw R1. Badly, it turns out. Get rid of I1. And now let's add in the voltage source due to RF. And we'll see what noise we can expect due to this voltage source. So we are now finding the output due to oh, whoops. I got too excited and sort of skipped a step. It turns out, going back a minute, I'm sorry, that the voltage VF across RF, and this again is for the case where we're looking at V1 being the only voltage source there, because this point here is 0 volts, and that means that V0F is equal to the voltage across RF, which in this case was minus V1 RF over R1. Okay, I apologize for having left that step out. I was so excited to go on to the next one that I just sort of got ahead of myself there. Okay, so here we'll make all this stuff just kind of go away. Okay, so finally, and let's actually do this in a different color so we can keep it straight. We now have this voltage VF, which is the voltage generated by RF. Okay. Again, we have that the voltage at the inverting input is 0 because V plus is equal to V minus. And if we have 0 volts across R1, that means that the current I1 has to be equal to 0 as well. Because if the voltage across the resistor is 0, the current is 0. And since no current is flowing into the inverting input, I minus is still 0, that means that the current through RF is also 0. Which means then that I've made another mistake. I'll correct it in just a minute. It means that V0F, okay, so this is the output due to the noise generated by RF, is 0 volts. I started 0 volts here, going up this way. I have just VF. So the output due to RF is VF. And this should have been V01. Okay. So I've made a mess of things, but this is basically what we need to have. We now know the output voltage due to the op-amp, the output voltage due to R1, and the output voltage due to RF. And in the next and hopefully last video, we'll combine those at the output and see what it all means.